Good evening, everyone. My name is Marc Jourdan. Today I'm going to present to you our work entitled Efficient Pure Exploration for Combinatorial Bandits with Semi-Bandit Feedback. This is a joint work conducted at ETH Zurich with Mojmir Mutny, Johannes Kirschner, and Andreas Krause. Before delving into the specific, let's look at an example in order to fix our ideas. Here, we consider a routing network problem where a network manager wishes to assess the quality of his network by sending a packet of information from his laptop to a given server. The environment, which is a graph, is modelized by a multi-arm bandit, where edges of the graph are arms associated with an unknown probability distribution on the latency of the connection. In contrast to standard bandit approach, the agent can only interact with the environment by playing actions, which are sets of arms satisfying a certain structure. So here, it's basically playing paths in the graph. Since we are in a routing protocol, we have access to timestamp data per edges in the path taken by the agent. Therefore, we are in the semi-bandit feedback setting. We are interested in answering the following question. What is the worst connection in the graph in order to fix it? Because we are a network manager. Due to the combinatorial nature of the problem, we need to assume the existence of an efficient oracle in order to sample the next action. Here, since actions are paths, we'll use Dijkstra algorithm. More formally, in combinatorial bandits, the stochastic environment is constituted of an unstructured D-arm bandit characterized by an unknown mean parameter mu in Rd. The agent can only interact with the environment by playing actions which are sets of arms satisfying a certain combinatorial structure. At time t, the agent chooses an action at and observes semi-bandit feedback, meaning it observes one value per arm inside the played action. The joint distribution of this vector is assumed to be the independent product of one parameter exponential family with mean mu a. Due to the combinatorial nature of the problem, we might have exponentially many actions. Therefore, we need to assume the existence of an efficient oracle in order to solve the following linear optimization problem over the action set. In the pure exploration framework, the agent gathers information to answer a given query, while disregarding the accumulated cost. Here, we are interested in identifying the best answer for the linear reward mu. Answers are sets of arms satisfying a certain combinatorial structure. Could be identifying the best arm, the best action, or the best something else. For example, in our previous example, it could be identifying the best spanning tree of the graph by applying paths in the graph. A pure exploration strategy is defined by three rules. First, a sampling rule, which tells the agent which action to sample next. Second, a recommendation rule, which gives the candidate answer would the algorithm stop. And third, the stopping rules, which dictates when to stop and output the candidate answer. In terms of objectives, we consider the fixed confidence setting, where one wishes to minimize the expected number of pools necessary to identify the correct answer with a confidence parameter delta. An additional important objective is to have computationally efficient implementation. The applications of this setting are numerous. As we have seen, the routing problem, but also batch experiment, where an experimenter evaluates k arms at the same time and wishes to identify either the best arm or the top k arm. A more exotic application is a protein design setting, where the experimenter wishes to identify the best protein, but for experimental reasons has to evaluate simultaneously 20 proteins. In this context, the contribution of our work are threefold. First, we use the game approach for pure exploration, which was introduced by Doge et al. In order to study combinatorial semi-bandit with arbitrary power set of actions and power set of answers. Second, we develop a combinatorial game meta-algorithm whose instances are asymptotically optimal algorithms with finite time guarantees. Third, and most importantly, we derive the first computational efficient algorithm for best arm identification, which is simultaneously asymptotically optimal and has competitive empirical performance. Since we are going to use a game approach to per expression, let's first understand where this game comes from. This game appears as a theoretical lower bound on the sample complexity. The following theorem, which is an adaptation of existing results to our setting, states that given a confidence parameter delta, for all delta pack strategies and all bandit nu, then we have that the sample complexity is lower bounded by a characteristic time multiplied by ln 1 over delta. This holds both for the finite time and the asymptotic regime. The inverse of the characteristic time, d nu, is a max-min optimization problem which dictates the complexity of the setting. Basically, the intuition behind it is the following. Defining an alternative parameter as a parameter such as its best answer is different from the one of the true parameter mu, we say that d nu represents the extent to which the true parameter mu is different from the most confusing alternative parameter lambda with respect to an information criterion. This information criterion is basically a Cal divergence, which is reweighted by the allocation over arms. The complexity d nu is achieved for the optimal allocation over arms such that it's the easiest to differentiate the best answer for the true parameter mu. Our proposed game meta-algorithm aims at approximating this game sequentially. Since the true parameter mu is unknown, we use the plugin maximum likelihood estimator mut. As regards the recommendation rule, the candidate answer will be the best answer for the current estimator. For the stopping rule, we use a generalized likelihood ratio test. Finally, for the sampling rules, which is the most important one, we will consider a two-player zero-sum game. First, the A player, which is a max player, will play pooling proportion over actions based on an online learner. Second, the lambda player, which is the min player, will play the most confusing alternative parameter using a best response oracle, which has access to the information of the played pooling proportion over actions. As algorithmic ingredient for our sampling rule, we use tracking in order to obtain a deterministic action from the played pooling proportion over action. We will also consider the praised principle of optimism in face of uncertainty and define an optimistic reward per arm. Finally, the online learner of the A player will aim at minimizing the cumulative regret for the linear regret reward RT. Depending on the choice of the learner, it will either update the pooling proportion over actions, which belong to the high-dimensional probability simplex, or it will directly update the effective pooling proportion over arms, which belongs to a 0-1 convex polytope in RT, which is the image of the simplex by an incidence matrix WA. In the following table, we compared 4 online learners to instantiate our game meta-algorithm. Even though the learner on the simplex, edge and ADA edge, achieved optimal cumulative regret in square root of t, their computational cost scales with the number of action and have a pooling proportion over action which is non-sparse. When the cardinality of the action set grows exponentially with the dimension, this is a major problem. In contrast, the learner on the transform simplex, online Frank-Wolf and LLO, are sparse, and their computational cost scales roughly with the support of the cumulative sum of pooling proportion over action. Therefore, they are computationally efficient. It is worth noting that LLO provides optimal cumulative regret guarantee, while online Frank-Wolf doesn't. Our game meta-algorithm satisfies the following theoretical guarantees, which states that given a parameter mu belonging to a bounded set and an online learner with sublinear regret, then the instantiated game meta-algorithm is asymptotically optimal, meaning that the upper bound for the asymptotic regime is the same as the lower bound. The finite time upper bound, which allowed to derive this result, is omitted from this presentation for the sake of time. For our experiment, we considered best arm identification by playing batches of size k equals 3 for a Gaussian bandit. We average our results over 750 REN and consider a confidence parameter delta equals to 0.1. This example is of particular interest because the number of actions is growing exponentially with the dimension d of the bandit, while the ratio of informative actions is decreasing harmonically. An action is said to be informative if it contains the best arm. On the left graph, the empirical stopping time is plotted as a function of the dimension d of the bandit, while on the right graph, the running time in milliseconds per iteration is displayed. We will plot one curve per learner in order to instantiate our Combinatorial. Unsurprisingly, uniform sampling, the black curve, has suboptimal sample complexity. ADA edge in red and edge in green both achieve better sample complexities than uniform sampling, with ADA edge slightly outperforming edge. Unfortunately, both of them have high computational costs, scaling exponentially with the dimension d of the bandit. This computational inefficiency is solved by unlike Frank-Wolf in brown, since it has low and almost constant computational cost. Unfortunately, it has suboptimal sample complexity. Achieving the best for both criterion, we observe that LLOO in blue has competitive sample complexity for a low and almost constant computational cost. To summarize our work, first, we develop an asymptotically optimal COM-game meta-algorithm for transductive combinatorial semi-bandits. Second, for the special case of best arm identification by playing actions, we derive the first computationally efficient algorithm, which is simultaneously asymptotically optimal and has competitive empirical performance. I thank you for your attention.